As I told you last time we talked about the complex numbers in polar form, there is one mathematical thing that we can do with complex numbers in polar form that we cannot do in a plus bi form. So I'm going to take a look at that. So first of all, I want you to recall our, some simple equations involving powers. So if we have x squared equals 1, hopefully you remember that in order to find the answer, we take the square root of both sides, and we have to remember that there are two square roots, a positive one and a negative one, so we always say plus or minus, and so x is plus or minus the square root of 1, which is plus or minus 1. So we have two square roots of 1. Now when we say x to the fourth equals 1, when we take the fourth root of both sides, or raise it to the 1/4 power, we also remember that since it's an even root, you were also taught that you do plus or minus. So plus or minus the fourth root of 1, which gives me plus or minus 1. However, can you think of any other numbers that if you raise them to the fourth power, you would get 1? Particularly think of an imaginary number. And you're thinking, oh, that's right, I squared is negative 1, so I to the fourth is equal to 1. Very good, I'm glad you thought of that. So I would also be a number that if you raise it to the fourth power, you would get 1. And it turns out also negative I, because negative I to the fourth is the same as positive I to the fourth, since it's an even power. So positive or negative I. So notice there are 4 fourth roots. Now if we have x to the third equals 1, obviously this is an odd root, so we don't do plus or minus, and so obviously one of the answers is 1. But you might be suspicious after what I just did with the fourth roots that there really are more than just one cube root. As a matter of fact, there are actually 3 cube roots. There are 3 cube roots. So what is the other one? I'm not sure why I'm writing in red. It probably doesn't show up as well. But the other 2 are complex numbers. And it turns out that the only way we can find them is by using polar form. So just to sum up, in general, every complex number has n nth roots. In other words, 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, etc., etc. And for most numbers, we can only find these roots by writing the complex number in polar form. So what I've done for notes today is rather than having you write a ton of stuff and try to keep up and listen, I've written out the notes for you for the most part. We'll add a few little things here and there. And I just want to explain the process to you. So I want you to follow along with your notes, and you might want to have out some sort of a bright colored marker or pen to mark certain things in something other than black or pencil so it kind of stands out. So first of all, how to find roots of a complex number. You might recall that we did a formula for powers. A power of a complex number, z to the n equals r to the n cosine n theta plus I sine n theta. So we raise r to the nth power and we multiply theta by n. Also recall that a root can be written as a power. So if I say the nth root of z, that's the same as saying z to the 1 over n. So like the square root would be z to the 1/2, the cube root would be z to the 1/3, the fourth root z to the 1/4, and so forth. So this follows the same pattern, so I do r to the 1 over n cosine of 1 over n times theta sine of 1 over n times theta. So this is in general how you would find a root of a complex number. But that only gives one of the roots. To get the others, we need to use coterminal angles. We need to recognize that if I have my number in polar form, cosine theta plus I sine theta, I could also say theta plus 2 pi and get another name for the same complex number, because theta plus 2 pi is in exactly the same position as theta is. It's just around the circle one more time. So I can keep adding multiples of 2 pi to theta and get additional angles that are exactly the same, or additional complex numbers that are exactly the same as my original number. So what I'm going to do is use k equals 0 with my original angle theta plus 2 pi times 0 would give me my first root, and then just keep adding 2 pi to get additional roots. So let's do this with an example. I want to find the cube roots of negative 27. In other words, I'm talking about solving the equation x squared or x cubed equals negative 27. So I want to find the cube roots, the three numbers that when multiplied times themselves give me negative 27. I guess I did already do that over here. The first thing I want to do is write negative 27 in polar form. And so you have to recall that negative 27 is to the left on the horizontal axis, which means in polar form we're talking about something that has a radius of 27. That's very hard to see. I'll try this again. So this is negative 27. R is equal to 27, and our theta is an angle. This is pi, because we're going around to, what, 180 degrees. So in polar form, z equals 27 cosine pi plus I sine pi. Now I want to find the cube root, so I'm going to raise it to the 1/3 power. So let me move this up a little bit so I'm at the top here. So z to the 1/3 equals 27 to the 1/3, and then I multiply the angle by 1/3. So I end up with 3 cosine pi over 3 plus I sine pi over 3. Familiar looking complex number in polar form. That's just the first root. So I'm going to put a box around this and say that this is root number 1. Oh dear, I've got something that's here that is not supposed to be here. Oh, I've got to pause and fix my document. Okay, that's better. I got to my document and found I didn't have all of it there, and I'm still have something that's kind of in the wrong place. So let me fix this. I copied something twice. There we go. That looks better. All right, now we're fixed. Okay, looking at step number 3. What I'm going to do is add 2 pi to the original angle pi. So I notice my original angle is pi, so I have plus 2 pi in both of those spots, and apply the formula again. So I have 27 to 1/3 cosine of 1/3 now times 3 pi. So 1/3 times 3 pi, which is pi. So I end up with 3 cosine pi plus I sine of pi. So this now is root number 2. One more root to go. I need to have 3 cube roots. So I add another 2 pi to my original angle. So instead of adding 2 pi, now I'm adding 4 pi. So I added pi. I have pi plus 4 pi, which is 5 pi. I did 27 to the 1/3, which is 3. 1/3 times 5 pi is 5 pi over 3. So here is my root number 3. Now what happens if I forget to count or something, or just out of curiosity, what happens if I do this a 4th time? So what happens if I add 6 pi now instead? Well, it turns out I end up with 1/3 of 7 pi, which is 7 pi over 3, but 7 pi over 3 is 6 pi over 3, which is 2 pi, plus another pi over 3. Basically, this is the same angle. 7 pi over 3 is all the way around the circle and back to pi over 3. So this is the same as pi over 3. It's coterminal. So this is the same as root number 1. So we basically started over again. And we don't need this one. And this is what happens each time if you have an integer power, that this will happen. It'll just start counting. It'll just repeat itself. It'll go on top of itself. Now, something that's useful is then also, and something I'm going to be asking you to do, is to put this number into rectangular form. So I want you to recall that in order to put this in rectangular form, I distribute the 3, and I have z is equal to 3 cosine pi over 3 plus 3 sine pi over 3i. And then I just have to figure out what cosine and sine of pi over 3 is. So I make my little triangle. And my angle pi over 3 is the same as 60 here. So I have a 30, 60, 90 triangle. And opposite 60 would be square root of 3. Opposite 30 would be 1, and this would be 2. So to find cosine of pi over 3, cosine of pi over 3 would be 1/2. Sine of pi over 3 would be square root of 3 over 2. So z is equal to 3 times 1/2 plus 3 times square root of 3 over 2I, or 3/2 plus 3 the square root of 3 over 2I. So in rectangular form, that's what it would look like. And if you flip over to the next page, you will see I have the 3 roots listed in polar form, and then I have the 3 roots listed in rectangular form. Notice that cosine pi plus I sine of pi, this would just be pi units, 3, radius of 3 in the direction of pi, that would just be -3. I could also think of that as 3 cosine of pi would be -1 plus I sine of pi would be 0. And so that gives me -3. If I look at the third one, I recognize that with pi over 3, now I'm in the fourth quadrant. So 5 pi over 3 is going to do the same process as we did with pi over 3, because this is still going to be a 30, 60, 90 triangle. But instead, the square root of 3 part's going to be negative. So that's why we have a negative sign here. So that's putting them all into rectangular form. Now we're going to plot these roots in polar form. And I want to show you something interesting when we plot them in polar form. So we have our pi over 3. So I'm just going to write pi over 3. R is equal to 3. Then we have our 3 times cosine of pi. So there's our second one is over on the horizontal axis to the left. And then we have 5 pi over 3. This is our 5 pi over 3, and this has a radius of 3. I want you to notice that these angles are all equally spaced. They're all 120 degrees apart, or 2 pi over 3 apart. So these are equally spaced. And this will always be true of the roots. Roots are equally spaced on the polar grid. So if I had 4 roots, you would expect them all to be 90 degrees or pi over 2 apart. If I have 6, they're going to be 60 degrees or pi over 3 apart. So in this case, 120 degrees or 2 pi over 3 apart. So that's something you'll always notice. Now I want to do a little calculator work, and then we'll be ready to explain what your homework is for the evening. So if you go to your calculator, let's check our work using the calculator. I want to show you a couple nifty things that your calculator will do. So adding a calculator page, and I also want to show you a tip about the I. I've been typing the I in wrong. I found out yesterday, after a great deal of frustration, what I was doing wrong, so I want to share that with you. Let's double check. We said that these 3 numbers were all cube roots of -27. That means if I raise them to the 3rd power, I should get -27. So let's do that in both polar form and rectangular form. So in polar form, I'm going to start by opening a set of parentheses because I want to raise it all to the 3rd power. And I've got cosine of pi over 3. And you know what? I'm slow typing, so I'm going to pause and type this in, and I'll come back to you. And you go ahead and pause, and you go ahead and type in the problem. Actually, I need to tell you something right now. One of the problems the problem that I had with I, if you use I from the keyboard down here, that's just a variable that you could call I. But the actual imaginary unit has to come from one of our menus. And if you go to the pi menu, you'll see that it's right next to pi. And notice it looks bold when you type it. If it doesn't look bold when you type it, then you've typed the wrong thing for I. Then I'm going to go trig, get my sign, and then I'll do pi divided by 3. And then I'm going to raise that to the 3rd power. Voila, -1. But guess what I forgot to do? I forgot the whole times 3 thing, didn't I? That's not what I wanted. So let me do this again. This is pretty easy fix. 3 times, and then I'll go up and capture this thing. Enter, and get rid of my cubed here. Delete that. Okay, so let me see, count my parentheses. 3, open, open, close. Okay, now this whole thing to the third power, this should be what I want now. Yay, there we go. So you can see then that this actually does equal negative 27. Now let's do the same thing in rectangular form. So open a set of parentheses, and I have 3 over 2 plus 3, the square root of 3 divided by 2 times I. And remember, once again, get the imaginary unit from the menu, and then raise that all to the third power, and enter, negative 27. Okay, so let me show you one other thing that your calculator does that is really nice, and that would be if I take this number that I have in this part right here, and I'm going to get rid of the cube root part. I'm going to delete that. And I guess I could actually delete that extra parenthesis too. Wait a minute, going too far. Come on, come on, come on. We'll delete one set of parentheses. It's not letting me do this. Okay, never mind, it's not behaving correctly. But if I do a control enter here, no, I just want to do enter. Notice if I type it in polar form and just push enter, it writes it in rectangular form for me. Very nice indeed. Make sure that you can show me trigonometrically also why this works. If you only use your calculator to find this, but you don't know how to find it yourself using a right triangle, then you will not do well on the test. So make sure you can certainly do this on the calculator. Make sure you also know how to do it by hand. Okay, back to our Smartboard presentation here. Okay, what do I want you to do for homework? Your homework is to do the following problems and then check the key on Google Drive. I'm going to put a complete worked out key on Google Drive, and it's going to be entitled Key to DeMoivres Theorem. I will also put a video with some homework tips on it, as well as a separate video of the lecture notes. The reason I'm doing this is because I want you to come in tomorrow already knowing what you know how to do. I want you to come in tomorrow already having checked your homework, be ready to review for the test because we will have a test coming up. So make sure that you go back and check this and make sure you're doing it right. I should see all work correctly shown because you can check it and you can make corrections on it if it is wrong. I also caution you that if you merely open up the PDF and copy it down, I might not be able to tell the difference. However, it will definitely show up on your test. So that would not be a good learning exercise to do that. Now, what do I want to see? First of all, put the number in polar form. So each one of these is given in a non-polar form to start with. You need to put it in polar form. Remember that if it's just a single number, that it's on one of the axes. 0, pi over 2, pi, or 3 pi over 2. If it's a number like 3 plus 4i here, you have to use your formulas. R equals the square root of a squared plus b squared and inverse tangent of b over a, etc. to do those. Then find all the roots in polar form and plot them. So that's when I say plot them, like this little show that how they're equally spaced and where they all are located. Thirdly, put the roots into rectangular form. So that would be like these down here. Put them into a plus bi form. And then fourth, check them by raising them to the indicated power on your calculator. Now, number 2 and number 4 are just square roots. There's just 2 of them. Number 3 has 3 cube roots. Number 1, though, has 8 roots. And so I don't expect you to show me by hand every single one of those, but you should show me by hand how to put one of them into rectangular form. You should at least check one of them or so on your, 1 or 2 of them on your calculator. Make sure that if you raise them to the 8th power, they actually do give you 1. If they don't, you've done something wrong. And the same thing with these. So do some of them by hand at least, and then you can kind of see a pattern going, and you can use your pattern to help you find some of the other ones if you want to. Do what work you need to make sure you know how to do all of these skills as I showed you in the notes. Make sure to put them on a separate sheet of paper because I did not give you enough room to do them on this sheet. Also, number 4, you will have to use decimals, so don't round when calculating. In other words, you'll have to round, obviously, when writing them down on a piece of paper. You'll just have to write down a few of the decimal places. But in your calculator, always go back and grab the original number so that when you get your final answer, it's not rounded at all. You'll be surprised how nicely it will turn out when you do that. Okay, go ahead and enjoy your homework.